Hi, welcome to today's astronomy video about dark matter, the mystery of dark matter. This is a nice overview of particle physics. At the left, these are the particles atoms are made of, the quarks. From them you can make baryons, then are the components of the nucleus of the atom, and the leptons, electrons. Together they make the atoms. The atoms make bonds, and you have the molecules. At the right, you have the four fundamental forces of physics and carrier particles like bosons, photons. And the physicists want to get here to the theory of everything, which unifies all four fundamental forces. It's a beautiful picture of the triangulum galaxy M33, which is located at a distance of 2.7 million light years. It is a member of the local group of galaxies together with Andromeda and the Milky Way galaxy. Its size is 61,100 light years. Its mass is 50 billion solar masses, which makes it number 3 after Andromeda, number 1, Milky Way, number 2. You can see one difference. This galaxy is unbarred, or it could have a very small bar. And it is a very bright galaxy. The reason is it has a high star formation rate. This is the rotation curve of the triangulum galaxy M33. This was expected from the visible disk, something like comparable to the solar system. The outer planets are lower, have lower orbital speed than the inner planets, but this was observed. So the outer stars in the triangulum galaxy and or other galaxies move too fast. This is another animation of the rotation curve. This was expected. Outer stars with lower orbital velocity, and this was measured. So the outer stars with about the same orbital velocity as the inner stars. They are too fast. And this is the current theory that explains this phenomenon. That's the artist's image of the dark matter halo around the Milky Way galaxy. The Milky Way galaxy, which with its stars is embedded in this halo of dark matter. There was a Gaia mission measurement of the mass of the Milky Way. The new number is 200 billion solar masses. And it is because of the dark matter that gives the galaxies its structure, and galaxies can maintain the structure only because of the presence of dark matter. This is the energy distribution in the universe. You can see at the left about 68% dark energy, which expands the universe in the large scale. 97% dark matter. Dark matter is known for its lack of interaction with light. It only interacts gravitationally, and the ordinary matter makes only 5%. This is the galaxy rotation in the nearby and distant galaxies. The left, that's the nearby galaxy. The dark matter has migrated towards the inner regions. That's why the outer stars move faster. And the distant galaxies, old galaxies, the dark matter is distributed more evenly. That's why the outer stars travel slower. Dark matter also explains the filament structure of the universe, because now you have enough matter to make these filaments. This is an evolution of a box of 140 million light years. This is a simulation. The gravity of the dark matter is essential for forming the filaments of galaxies and clusters, and the big empty spaces in between. They are called voids. So dark matter is also essential for life because it keeps the galaxy together. And the material from the nuclear fusion of the previous generations of stars, which is ejected into space by the supernova, is held in the same galaxy, and that makes the formation of new generations of stars and planets possible, and eventually formation of life. This is a 3D map of the dark matter distribution, which is in clumps. This rules out the neutrino as a dark matter particle. First, it is too light. All the neutrinos in the universe can't be make more than 1% of the matter. And second, it is too fast, it can't clump. And other weakly interacting mass particles, WIMPs, were not found yet either. There's another dark matter map by the Hyper Supreme Chem survey from 2018. There's another theory, that's the MONT theory, modified Newtonian dynamics. It says that there are different laws in the galactic scale. This is the bullet cluster 1E0657556. It's a composite image of Magellan and Hubble. It is at a distance of 3.7 billion light years. And the indirect detection of dark matter in this picture in blue by gravitational lensing combined with the X-ray detections in pink. And this bullet cluster contradicts the MONT theory. There's another candidate for dark matter, MACHOs, called massive astrophysical compact halo objects. And one candidate of MACHOs could be primordial black holes. Other candidates could be brown dwarfs. But this theory is not consistent with the observed element and isotope abundances, for example, of the isotope deuterium. This animation of a particle, another hypothetical particle, that's the XENONnT. It is a particle of cold dark matter. Cold means slowly moving dark matter, but this particle is not detected yet. There's another theory, that's the hairy dark matter. According to this theory, Earth is embedded in a filament of dark matter. This particle is called hairs and pass through Earth. How can you measure dark matter? How can you detect it? This is one research project. It's called XENON. That's the detection of WIMPs, weakly interacting massive particles, by their scintillation and ionization. And for this, liquid xenon gas with liquid xenon with gas phase on top is used. And you need an electric field to extract the electrons. At the top and at the bottom, there are two arrays of photomultiplier tubes called PMTs. There's another project called DAP 3600. It's a dark matter experiment. It uses a argon pulse shape discrimination. And it works with 3,600 kilogram liquid argon. In this picture, you can see the 2-meter diameter spherical acrylic vessel contains 255 photomultiplier tubes. This vessel is placed inside a 7.8 meter diameter shield tank, which contains ultra pure water. The water filters out the other particles that are not useful for this experiment. And again, this experiment also works with scintillation of that is a detection for dark matter. Scintillation is a emission of UV light or visible light from the interaction with these particles with the argon gas, argon atoms. This is a nice picture. It's called Hubble History Book. It's a picture of 265,000 galaxies. It stretches back to just 1/2 billion years after the Big Bang. And at very big scales, there's another phenomenon that is totally dominant, that's dark energy. And it works against gravity and causes an expansion of the universe at a very big scale. And like dark matter, dark energy is also unknown. This is a nice picture of a shower from a cosmic particle, which was registered in a calorimeter detector. It's a very nice picture, looks almost like art. That was today's video about the mystery of dark matter. I think this mystery will be solved in the near future because you have better and better telescopes, better and better detectors. Yeah, that's very interesting, and you can check out the links in the description field. Thank you for watching. Have a nice day. Bye-bye.